Hello, and welcome to The Space Above Us. Episode 104, Space Shuttle Flight 33, STS-32. Longer Duration Exposure Facility. Last time, we talked about the secretive flight of STS-33. As usual with classified missions, we sort of poked around the edges to try to guess what it could be about. We also maybe took classified too literally and skimmed through the classifieds section of the JSC News Roundup newsletter to see how much computers cost back then. Today's mission will not be classified, and also presents us with an opportunity to dig into a bunch of juicy flight dynamics details. But first, we have a little housekeeping to do. This was actually announced during the flight we'll be discussing today, but let's take care of it now. Allow me to introduce to you, dear listeners, Astronaut Group 13, the Black Cats. On the pilot side, we've got Kenneth Cockrell, Eileen Collins, William G. Gregory, James Halsell, Charles Precourt, Richard Searfoss, and Terrence Wilcutt. And on the mission specialist side, Daniel Bursch, Leroy Chow, Michael R. Clifford, Bernard Harris, Susan Helms, Thomas David Jones, William MacArthur, James Newman, Ellen Ochoa, Ronald Sega, Nancy Curie, Donald A. Thomas, Janice Voss, Carl E. Waltz, Peter Wissoff, and David Wolf. Notably, Eileen Collins was the first woman selected for the pilot track of the shuttle program, and she would indeed become the first woman to serve as pilot and as commander for the space shuttle. We'll be seeing plenty of Eileen Collins in the episodes to come. The Going the Distance award for this group goes to David Wolf, who had the latest last flight in this group, flying on STS-127 in July of 2009. Also, while it's not this one, I know that there's a David Wolf listening, so hey David. Speaking of going the distance, on April 7th, 1984, the grapple mechanism of Challenger's remote manipulator system retracted. Shuttle Commander Bob Crippen gently fired the smallest available thrusters to back the orbiter away, and the Long Duration Exposure Facility's mission was underway. We covered this way back on episode 78, which followed STS-41C on a pretty dramatic flight. As you'll recall, after dropping off LDEF, Challenger continued on to rendezvous with the Solar Maximum mission, which could have gone more smoothly. I'll leave most of the details back in episode 78, but since it's been over a year, and since it's going to be pretty relevant to today's topic, allow me to quickly refresh your memory on LDEF. The Long Duration Exposure Facility was basically what it sounded like. It was a facility for exposing material to space for a long period of time. 30 feet long and 14 feet across, it was roughly cylindrical, but instead of a circle, it had 12 sides. Oh man, this is another opportunity for me to use the phrase dodecagonal prism, because that's what LDEF was, a dodecagon sort of stretched out into a 3D shape. Dodecagonal prism. Covering the sides of the spacecraft were 86 different experiment trays slotted into the main structure. These experiments would take advantage of the lengthy flight to learn more about how various materials held up in space, the makeup of interstellar gas, cosmic radiation, micrometeoroids, and even what being in space did to 12.5 million tomato seeds. By the way, you can actually buy these tomato seeds on eBay, but they cost a little more than the STS-8 postal covers I mentioned way back when. Notably, the spacecraft did not contain any sort of power, propulsion, or attitude control systems. Instead, it would rely on gravity gradient stabilization, naturally aligning its long axis to be perpendicular to the Earth. By remaining completely passive, LDEF served as a stable and predictable platform for science. There were no vibrations from thruster firings or astronauts bouncing around. But as we'll see, it also made retrieval a little tricky. LDEF was originally supposed to be retrieved by STS-51D in early 1985, after almost a year in space. That was eventually bumped to STS-61I in September of 1986. Of course, after the Challenger accident in January of 1986, the shuttle fleet was grounded, and LDEF had to continue to wait. That wait ends now with STS-32. Once the shuttle returned to flight, there were a number of high-priority missions that had to be carried out before LDEF retrieval could be considered again. But the clock was ticking. LDEF had been deployed into a circular orbit with an altitude of 509 kilometers. But it wouldn't stay there. As the weeks, months, and years ticked by, the tenuous upper atmosphere did its thing and started to lower LDEF's orbit. It didn't help when, starting in 1987, increased solar activity fluffed up the upper atmosphere, further increasing the drag and further lowering the orbit. By the middle of December 1989, LDEF's orbit had lowered to only around 330 kilometers, down from 509, and it was losing a kilometer or so every day. Once its orbit reached 300 kilometers, it would be too late. The forces of atmospheric drag would start to overcome the gentle gravity gradient effect that kept LDEF stable, and the spacecraft would begin to tumble, making retrieval impossible. If Columbia and its crew couldn't get to LDEF in a matter of weeks, we'd be looking at the failed shuttle Skylab rescue all over again. The pressure was on. Commanding the flight was Dan Brandenstein, who we last saw commanding STS-51G back in 1985. This is his third of 4 flights, but this one was extra special since he'll actually celebrate his 47th birthday during the mission. Joining Brandenstein up front was our pilot, Jim Weatherby. James Weatherby was born on November 27, 1952 in Flushing, New York. He earned a bachelor's degree in aerospace engineering from Notre Dame before joining the Navy a year later. He pulled off 345 carrier landings, 125 of those at night, before heading off to the U.S. Naval Test Pilot School. From there, he moved on to systems engineering, serving as a test pilot and a project officer for various subsystems of the F-18. NASA picked him up in 1984, and this is his first of 6 flights. Mission Specialist 1 was Bonnie Dunbar. We know Dunbar from her flight on STS-61A, which carried Spacelab and set the record for the largest shuttle crew size, stuffing 8 people into the orbiter. I should also mention that one of her crewmates on that mission was Vubo Ockels, mostly just because it gave me another chance to say Vubo Ockels. Mission Specialist 2 was Marcia Ivins. Marcia Ivins was born on April 15, 1951 in Baltimore, Maryland. She earned a bachelor's degree in aerospace engineering from the University of Colorado and began working at the Johnson Space Center a year later, focusing on orbiter displays and controls, including the heads-up display. She later became a flight engineer on the shuttle training aircraft, and 10 years after arriving at Johnson, was selected as an astronaut in 1984. This is her first of 5 flights. And last but not least, Mission Specialist 3, David Lowe. George David Lowe, who went by his middle name, was born on February 19, 1956 in Cleveland, Ohio. He earned a bachelor's in physics engineering, a bachelor's in mechanical engineering, and a master's in aeronautics and astronautics. He worked at JPL for several years, working on, among other things, the Galileo mission and a Mars orbiter. He was selected as an astronaut in 1984, and this is his first of 3 flights. I promised myself that I wouldn't make a joke about David Lowe riding to orbit down on the middeck, but, well, here we are. STS-32 would be the first shuttle to depart from Launch Complex 39A since January of 1986, when STS-61C lifted off. It would also be the first shuttle to launch from Mobile Launch Platform 3, which hadn't been used since the Apollo program. Work on 39A had been underway for some time, and it was really a tight squeeze to finish the effort before STS-32's scheduled launch date of December 18, 1989. On November 28th, Mission Commander Brandenstein said, quote, "About a month ago, just about everyone around would not have guessed that Pad A would be ready." Well, turns out they were right, because it couldn't quite get the pad upgrades done in time. After a couple of reschedules, the flight was moved to the other side of the holidays and into the next decade. On January 8th, the countdown was underway, the crew suited up and entered the spacecraft, and attention turned to the first shuttle launch attempt of 1990. Unfortunately, no one really expected it to go anywhere. The chances of favorable weather were only around 10%, but the decision was made to proceed with the countdown anyway since they might get lucky, and if nothing else, it would serve as one more checkout for the upgrades to the launch pad. Sure enough, though, the launch was eventually called off due to unacceptable weather at the shuttle landing facility, which would be needed in the case of an RTLS abort. Finally, on January 9, 1990, at 7:35 a.m. Eastern Time, Columbia lifted off for the 9th time, and the chase to LDEF had begun. Ascent was uneventful, with no OMS 1 burn required, leaving Columbia in an initial orbit of 61 by 346 kilometers. That alarmingly low perigee would be raised by the OMS 2 burn just half a revolution later. One day and about 1 hour after lifting off, the first major event of the flight took place, deploying SYNCOM-4 F5. We've seen these SYNCOM satellites a few times now. These are some Hughes communication satellites that make their way up to geostationary orbit after being tossed out of the payload bay in a frisbee-like deployment. This particular SYNCOM spacecraft would be the 5th and final of a constellation used by the Department of Defense for communications. We thought we had already finished off this constellation, but the 4th spacecraft failed early, so this spare spacecraft was sent up to replace it. Considering that this constellation was leased by and used by the DoD, I'm not sure if this counts as a commercial spacecraft or not, but if it does, then I'm pretty sure that this is the last commercial satellite to be deployed from the shuttle. At least the last large commercial satellite. There might be some CubeSat or something I'm missing. I'm not actually completely sure about this, since it's tough to track down without reading ahead through the entire program history, but it would make sense. After the Challenger accident, commercial satellites were booted off of the shuttle, going back to expendable launch vehicles. But the SYNCOM series were designed specifically to be deployed from the shuttle, and they were being used by the DoD, so I could see how one last payload might have snuck onto the manifest. It really does feel like a weird relic from an earlier time, though. Normally, punching out one of these communication satellites would just be a bullet point on my outline and we move on, but there's something interesting about this one. As we've discussed, satellites typically have pretty constrained windows when they can be deployed. They're usually designed with these windows in mind so that they can squeeze every bit of performance possible out of the spacecraft. But in the case of SYNCOM-4 F5, they knew that they would be launching on the LDEF retrieval mission, which as a ground-up rendezvous would have far tighter requirements. With that in mind, the flight dynamics folks put their heads together and came up with 3 different scenarios that SYNCOM could follow, depending on when it would be deployed. There was the nominal scenario, which would be followed if SYNCOM's conditions were already met, a sub-transfer Earth orbit scenario, and a low Earth orbit scenario. Let's break them down. The nominal scenario is what we're used to. SYNCOM would be flung out on its way, deploying its antenna and spinning up about a minute and a half after leaving the shuttle. 45 minutes later, a perigee kick motor, a solid motor derived from the 3rd stage of a Minuteman missile, would raise its apogee to around 15,000 kilometers. After that, SYNCOM would use its own liquid propellant engines to execute a series of orbit raises before finally circularizing at GEO. Pretty typical stuff. The second scenario, sub-transfer Earth orbit, was pretty similar, except after firing the perigee kick stage, it would stay in that lower orbit for up to 20 days before continuing on with orbit raising. And lastly, the third scenario, low Earth orbit, is just what it sounds like. The initial perigee kick would be delayed, while SYNCOM drifted in low Earth orbit for up to 15 days. And then the rest of orbit raising would go like normal. Of course, my first question was, well, what's the difference between these 3 scenarios? Why dwell in a weird lower orbit for 20 days, or remain in low Earth orbit for 15 days? The answer is that the engineers were taking advantage of some real-world, non-idealized orbital mechanics to achieve the type of orbit that they needed. Normally, to figure something like this out, I'd need to go digging around through the sources and hope to find one that mentions what the difference was between the 3 scenarios. But I'm pretty lucky in this case, because my employer happens to make an extremely high-fidelity flight dynamics application used on numerous real-world space missions, FreeFlyer. And since I'm an employee, I can mess around with it in my free time to answer questions like this. I didn't know all the details of the nominal orbit raising campaign, so I decided to just compare the first parts of scenarios 2 and 3. I created 2 spacecraft and inserted them into the STS-32 orbit at the time SYNCOM was actually deployed. With one of them, I targeted a maneuver that would raise the apogee to the desired 15,000 kilometers after 45 minutes, and with the other, I just let it drift. I then plotted the Keplerian elements of both spacecraft over the course of 15 days to see what the difference was. What jumped out at me right away was that the orbit of the spacecraft in the middle orbit was slowly changing. Over the 15 days, its argument of perigee bumped up a few degrees, and its right ascension of the ascending node, or RAN, decreased by about 20 degrees. The always expensive to change inclination crept up by a few hundredths of a degree. If these terms don't mean anything to you, don't worry, they're just ways of describing the orbit. What matters is how it compares to the other scenario. In the low Earth orbit scenario, scenario 3, things moved much quicker. Instead of the argument of perigee increasing by just a few degrees, it increased by around 160 degrees. And the RAN decreased by around 110 degrees instead of 20 degrees. Perhaps most critically, the inclination changed around 5 times as fast as the middle orbit scenario. That was a lot of orbital mechanics, so I'll sum it up like this. The SYNCOM engineers were able to use these different scenarios to essentially turn some knobs on their orbit. So if the shuttle had to kick them out at a non-ideal time, one with the metaphorical knobs in the wrong place, they could use the imperfections of the Earth and real-world orbital dynamics to turn the knobs to where they needed to be before heading up to GEO. The middle orbit turned the knobs slowly, and the low orbit turned them quickly. But if the knobs were in the right place after all, they were able to follow the nominal scenario and could just head on up to GEO. Pretty clever. With SYNCOM gone, we can turn our attention to LDEF. We actually have LDEF and Solar Max to thank for a lot of the rendezvous procedures used by the shuttle. In the 1970s, analysts running the numbers realized that the attitude control thrusters on the shuttle posed a serious problem for rendezvous. The thrusters were placed and sized to ensure sufficient control authority during reentry, with rendezvous not really being considered. That resulted in a nice and stable spacecraft during atmospheric entry, but it meant that some pretty big thrusters were pointed in some pretty inconvenient directions. If Columbia approached LDEF in a way similar to how Gemini and Apollo missions did their rendezvous approach, it was likely to blast it into an uncontrolled tumble. Before the shuttle even started flying, a lot of work went into simulations and models to develop procedures that would allow for safe and stable rendezvous. This included a lot of sims with humans in the loop and actually flying on shuttle-like hardware. LDEF also presented a unique challenge in that its attitude wasn't controlled. The shuttle crew could expect the long axis to be perpendicular to the Earth, but it was able to gently rotate about that long axis. And since the two grapple fixtures were on the sides, not the ends, that meant that they would be at an unknown angle. We'll discuss how they solved that in just a moment. Rather than talk about all this in the abstract, let's get right into the actual rendezvous. In the days following the SYNCOM deploy, a few small maneuvers were performed to line up the rendezvous for Flight Day 4. This resulted in Columbia having roughly the same apogee as LDEF and a perigee that was around 9 kilometers lower. This meant that Columbia's orbit was smaller, making Columbia slightly faster, which meant that it crept up from behind LDEF. But since Columbia's orbit wasn't circular, from LDEF's point of view, it made a sort of bobbing up and down motion. If you were watching Columbia from LDEF, when it was 75 kilometers away, you would see it rise up to your altitude and then start sinking back down while continuing to move closer. It sank down 6 kilometers, but since it kept moving closer, it was now only 60 kilometers away, and then it started rising back up again. This strange relative motion was all a consequence of Columbia's apogee matching LDEF's, but its perigee being lower. The second time Columbia bobbed up to LDEF's altitude, it was around 45 kilometers away. A critical part of this rendezvous was the onboard radar, which is actually just the Ku-band antenna normally used for TDRS, which could provide the crew with range and range rate information. For orbital rendezvous, these are crucial numbers. How far away is the target? How fast are we getting closer? This radar was not expected to lock onto LDEF until they were around 38 kilometers away, but instead it locked on right now, 45 kilometers away. The radar signal looked good, so Mission Control decided to deviate a little bit from the plan and allow the shuttle's computer to start using the radar data while planning maneuvers. On its own, this isn't all that unusual. For instance, it wasn't uncommon for the landing radar on the Apollo lunar module to lock onto the surface early and be integrated into the navigation filter. Here's the problem, though. This radar had a little issue. There was a small range where the returned signal would look strong, but it would have a bias, essentially giving bad data. This issue was actually known to the since-retired designers of the radar, but since it only happened outside of the certified operational range, they didn't bother adding it to any documentation. So when Columbia bobbed back down 5 kilometers and calculated its next rendezvous burn, it was using this bogus data from the radar. When it bobbed up again, it was still around 20 kilometers behind LDEF, but instead of being 300 meters above it, it was now 1,300 meters above it. It had bobbed too high and too far back, making a total error of around 9 kilometers. So when it bobbed back down for the last time, and the crew began the final braking sequence, they had to brake a lot more than they expected in order to slow down. In the end, this ended up not being that big of an issue, thanks to the actions of the crew. But when you're talking about proximity operations being off by 9 kilometers, when you're only around 20 kilometers away, that's pretty scary. After the flight, the folks who designed the radar were tracked down, and with their help they figured out what happened. This all appears in a document called Lessons Learned from 7 Space Shuttle Missions, written by Space Shuttle Rendezvous expert John Goodman. No, not that John Goodman, the one who knows all about Space Shuttle Rendezvous. The lesson learned from this near incident was, quote, fully document the design and performance characteristics of sensors both inside and outside of the certified performance envelope, end quote. After all, you never know when a procedure might be tweaked or an unusual situation will call for a little extra performance. Once braking was complete, Columbia could move in for the final approach. Due to the grapple fixture location issue, LDEF could not be approached from the front or behind, an axis called the V-bar since it represented the direction of its velocity. Instead, Columbia would have to approach on the R-bar, an invisible line extending from the center of the Earth up through LDEF and out into space. But since the available sensors could not yet handle an approach on the R-bar from below, Columbia would have to drop in from above. So the orbiter first arrived on the V-bar around 120 meters in front of LDEF. It then sort of traced out a circle around LDEF. If you imagine that LDEF is flying from the right to the left and it's at the center of a clock, Columbia arrived around 9 o'clock and then traced out the edge of the clock to 12 o'clock. Columbia arrived 90 meters above LDEF before coming to a relative stop. At these close ranges, the thrusters that pointed towards LDEF had to be inhibited to prevent blasting it with exhaust gas. Instead, the orbiter switched to a mode called low Z. If they wanted to thrust up relative to the orbiter, instead of using the thrusters that pointed in that direction, they would instead fire thrusters that aimed forwards and backwards. In a lucky break for the rendezvous folks, these thrusters actually pointed very slightly up. So even though most of the thrust would be wasted by fruitlessly pushing in on Columbia, a little bit would go up, but in a direction that avoided LDEF. Now that Columbia was stationed 90 meters above LDEF, they could solve the problem of lining up with the grapple fixture. They were close enough that the crew could just look out the window and see where the grapple fixture was, and then yaw the orbiter around to line up with it. So imagine the orbiter is flying upside down and backwards, but now it's going to keep its payload bay facing the Earth and rotate in a flat spin so the grapple fixture is easy to grab with the robot arm. After all that, just short of 3 days and 3 hours into the flight, mission specialist Bonnie Dunbar reached out with the RMS and grabbed on. They had captured LDEF. But they weren't quite done yet. First, in order to protect the parts of LDEF that had not been exposed to the windward direction, they moved the orbiter to act as a big shield. At this altitude, the sort of air you run into contains free atomic oxygen, which reacts easily with materials. Since part of the point of LDEF was to learn more about this, it would be a shame to suddenly expose previously unexposed areas, hence the shielding maneuver. Next, the crew took a few hours carefully photographing every inch of LDEF, using the arm to move it around. This way, they'd be able to tell what, if any, changes were made in the process of returning LDEF to Earth. It also meant that scientists would still get some useful data if they had to cut LDEF loose again. I don't know how likely this scenario was, but if the latches in the payload bay failed to lock LDEF into place, they would have no choice but to redeploy it, though they'd boost it to a higher orbit first. Thankfully, the latches locked, and LDEF was finally on its way home. Its total time in space would end up being over 2,000 days. With all this happening on Flight Day 4, you might imagine that this is the part where I start talking about the crew suiting up and getting ready to head home. But actually no, we're not even at the halfway point of this flight yet. Columbia had been upgraded with an extra tank for the fuel cells, allowing for a significantly longer mission, with the target for this flight being about 10 days, making it the second longest shuttle flight so far. But that was just the start. The hope was to eventually get to flights of up to 28 days. But that raised an important question. Can an astronaut who just spent 28 days in space safely fly and land the shuttle? Skylab astronauts did that, but in the Apollo command module, they re-enter on their backs, and the entry was almost entirely automatic, especially the final splashdown. On the shuttle, the crews were sitting in a normal sitting position, which would result in blood being pulled down from their brains. And the commander had to manually fly the final critical moments of landing. So, as part of this lengthy mission, a number of medical examinations were done on the crew. The echocardiogram was flown again, and a version of Skylab's lower body negative pressure device made an appearance. Mission specialists Lowe and Dunbar took turns in the device, sealing it around their waist and spending several hours drinking water and allowing the fluids in their body to rebalance due to the lowered air pressure around their legs. Dunbar said she felt it made entry a little bit easier. Another interesting device was the Latitude-Longitude Locator Experiment, or L3. When payload specialist Paul Scully Power flew on STS-31G, he saw a lot of interesting stuff in the ocean, but was never completely sure what part of the Earth he was above. This made it really hard to follow up on these once the mission was over. L3 solved this with a clever mechanism and some trigonometry. If a crew member saw an interesting feature on the ground, they would point the L3 camera at it and take a picture. They would then track the feature, wait 15 seconds, and take a second photo. This data fed into a little computer that took the shuttle's current position, the two angles, and the time between the photos, and calculated the latitude and longitude of the target. I think it's important to point out this wasn't doing any sort of image recognition. It was just based on the timing and the trig. And the system was pretty accurate. It had a design goal of 10 miles, and a couple of sightings on this flight were within 3 miles. One nice little postscript on this device is that one of the folks heavily involved in its development was David Griggs, who was supposed to have flown on STS-32 but was killed in a plane crash just a few months before his flight. So though Griggs was gone, his work lived on. There were a few other interesting odds and ends on this flight, including a corrupt state vector being uplinked during the crew sleep period, resulting in Mission Commander Brandenstein waking up to an alarm and the moon whizzing past a window, a leaky humidity control unit resulting in big blobs of water under the floor, a blockage in the wastewater dump line, and, of course, tags jamming again. But overall, the rest of the flight was uneventful and allowed the crew to focus on operating mid-deck material science experiments and crew-based medical experiments. The flight was upgraded from second longest shuttle flight to date to longest shuttle flight to date when heavy fog at Edwards resulted in one more day being tacked onto the mission. After an uneventful entry, Columbia touched down in a night landing at Edwards Air Force Base, 10 days, 21 hours, and 36 seconds after lifting off. With LDEF in the back, it was the heaviest landing so far. Orbiter, crew, experiments, and payload all added up to 228,335 pounds. Unfortunately, I don't really have a clean epilogue for LDEF. With dozens of experiments and lengthy scientific analysis to be done, there isn't any one thing I can point to and say, LDEF did that. But its lengthy stay on orbit would certainly have made an impact for future spacecraft, especially long-lived ones like the still being planned Space Station Freedom and the actually in space now International Space Station. By better understanding the long-term effects of atomic oxygen, direct exposure to unfiltered sunlight, micrometeoroids, and cosmic radiation, spacecraft designers could squeeze even more performance out of the projects they worked on. I can tell you, though, that the tomatoes grown from the LDEF seeds grew slightly faster than normal tomato seeds. So that's kind of neat. One thing I had trouble finding is, where is LDEF now? It never flew again, and as a big piece of space hardware with an interesting place in shuttle history, I expected to find it hanging from the ceiling of a museum somewhere, but I just can't find any trace of it. The closest I got was a completely unconfirmed forum post by a guy who said his boss had a piece of it on his desk. So if you know where LDEF is, shoot me a message. I've got to have at least one listener who works at NASA Langley. Next time. Okay, this is getting ridiculous. We have another classified mission. At least we can take solace in the knowledge that it's the second to last fully classified mission, but still. Oh well, even if we can't be sure what the payload is, we can still enjoy the beautiful launch. I'll try not to get too misty-eyed about it. Ad Astra, catch you on the next pass.